field psi. So we said that this can be thought of as a sum over all basis states in the Hilbert space of worldsheet CFT. And so you take one of the basis states phi s and then multiply it with a coefficient psi s, and then sum this over all possible states that are there in the worldsheet Hilbert space, satisfying the constraints B0 minus B0 bar phi s equal to 0. Also the operator L0 minus L0 bar should annihilate the states phi s. So you should select only those subsets satisfying these two conditions, and then sum over all those states with a coefficient multiplied to it. And the coefficient is a function of space-time coordinates. And this was the target space field for string field theory. So then we said that every single thing that you have in worldsheet.
It's not necessarily orthonormal.
I mean, it's a basis state. So you take the complete Hilbert space, and you have an orthonormality condition between these two, and so it could include everything: primary, non-primary, every single thing that you have in everything, including all those auxiliary states which are not physical from the string perturbation theory point of view. So this sum is much bigger than what you expect from string perturbation theory. So the phi s may involve states like gravitons and everything that appear in the Hilbert space or the spectrum of string theory, or it could be something which can be thought of as a gauge null state or even more. So in other words, usually in string perturbation theory, the states have Gauss number 2. So this could be something that have arbitrary Gauss number. So you are supposed to sum over all states that satisfy these conditions. And then we said that you have to identify fields and antifields. So for that, what we did is we denoted the basis state for Hilbert space as phi s, and the conjugate basis as phi c r, such that if I take an inner product between phi r c and phi s, that should be delta r s. So what we did is we took state from this conjugate basis and then multiplied it with a B0 minus, and we call this as phi tilde r. So what we did is we took these two bases and then represented psi as a sum of two string fields, and one string field which we denoted as psi plus has a summation, has an expansion like this, but the only difference is that you are supposed to take basis states from a collection of phi tilde r, and then in psi minus we took basis state from the phi s basis. And then we had, so then that means we could expand psi plus as phi tilde r multiplied with psi r plus, so which I denoted as psi star r, and then for psi minus we had a summation where we sum over all states coming from the basis phi s with coefficient psi s. And we had a condition that you should sum only over those states having Gauss number less than or equal to 2. And we had introduced a notion of Gauss number for target space field, so which was related to the Gauss number for the associated basis state. So you have Gauss number for psi s defined as 2 minus Gauss number for the basis phi s, basis state phi s. So that's equivalent to saying that you are assigning a Gauss number for fields, and then if the Gauss number for the field is greater than or equal to 0, you call them as the field for the BV quantization. And here, if you do you can do the similar thing, then imposing that Gauss number of basis states phi r is less than or equal to 2 is equivalent to saying that Gauss number for phi tilde r are such that it should be greater than or equal to 2, or in other words, the Gauss number for psi star r should be less than 0. So all the target space field having Gauss number negative, we identified them as antifields. So these are the fields and antifields for BV formalism. So once you have that, then we introduce notion of string product. So which was a mapping from Hilbert space, tensor product of Hilbert space. So you consider n Hilbert space and take the tensor product, and then the string product, take it back to the Hilbert space H. So it's a multilinear mapping from n product of Hilbert space to a single Hilbert space. So if I take n string fields psi 1 to psi n and then apply the string product, then I get a state that belongs to the Hilbert space of world sheet CFT. So this was string product, and the string product had a nice property. So we have to construct a product that satisfies the fundamental identity. So it's not an arbitrary product. It should satisfy a very stringent condition, and let me quickly write that. So it satisfies the identity n factorial divided by L factorial k factorial psi raised to L. That means you are inserting L number of psis, and then you have a string product with a k number of psi, and the string product is associated with a particular Riemann surface. So that means you have to associate the genus of that Hilbert, that Riemann surface to the string product. So you take k number of string fields and then evaluate the string product associated with genus G Riemann surface, G1 Riemann surface, and then put it into another string product associated with another Riemann surface. Then sum over n and L and k, where n is L plus k, and then you are supposed to sum over all G1 and G2 satisfying the condition G, that G1 plus G2 equal to G, and then you have one more term. So that is half of sum over basis states phi s phi tilde s psi n G minus 1. And then we said that this identity can be understood as a statement about string amplitude. So you start with a string amplitude at genus G level. So you have a G loop amplitude having n number of external states, and then we replace one of the external state with a BRST operator or BRST exact state. Then the whole contribution should vanish. And this statement, the fundamental identity, basically encodes this statement. So that's an important thing that string product has to satisfy. And then we defined a string multilinear function which can be obtained from a string product. So you take the string product and then, which is a state associated with the genus G Riemann surface with some number of insertions, and then take an inner product with another state A, then that produces a number, a complex number, which can be thought of as a correlation function that you compute on a genus G Riemann surface with world sheet CFT. Now again, this identity, the fundamental identity, will induce a similar identity for multilinear functions, and you get similar relation replace with square bracket replaced with this bracket. And then we said that if you can construct such string product and string multilinear function, then one can define a string field theory action. And the string field theory action has a simple form. So the at classical level, the master action has the form 1 by gs square, and then sum over n runs from 2 to infinity, gs raised to n divided by n factorial. Then you have to consider multilinear function associated with genus 0 Riemann surface with n number of string fields in it. And this is the string field theory action at the classical level. So if I expand this, you can identify a kinetic time here, psi q psi plus n running from 3 to infinity, gs raised to n minus 2 divided by n factorial psi n 0. So this is the kinetic time for string classical kinetic time and the set of interaction times. You can see that there are infinite number of interaction times even at the classical level, plus delta gamma psi, and gamma is the gauge parameter, and that's given by a string product gs raised to n divided by n factorial psi n gamma evaluated for a genus 0 Riemann surface with n running from 0 to infinity. So if you do such a field deformation, the action is invariant, where omega is another string field satisfying, which is annihilated by B0 minus and L0 minus. So this is the gauge invariance for string field theory action. So this is the place where we stopped. Now we would like to understand what is a gauge algebra. So for that, what we should do is we should consider two gauge transformations and then find the commutator. So you can evaluate this and then see that it has two pieces. One piece is again a gauge transformation, delta gamma psi acting on psi. I will explicitly write down what is this. Here one should note that the gauge parameter will start depending on a string field itself. So that's equivalent to saying that you have a gauge algebra where the structure constant is going to depend on the field itself. So it's not actually a constant. And then you have another piece where you have a field classical equation coming. Where f of psi equal to 0 is the equation of motion at classical level. So what you see is that the gauge algebra for string field theory is actually an open algebra. That means it won't close unless you use the equation of motion. So it's a open algebra which has a piece proportional to its equation of motion. So that means quantization of string field theory really requires BV formalism. So let me write what is delta Lambdazai. So Lambdazai is the gauge parameter which you get after taking a commutator as given by and again an infinite sum omega lambda 1 lambda 2 psi n 0 gs raised to n plus 1 divided by n factorial. So here you see that if you try to extract the structure constant, the structure function will depend on the field, the string field itself.
Haven't you observed this piece also into that?
Which one? Here. So see, here the difference is that we want to see that, so you have a field equation of motion coming, right? So that's an important observation.
Fair enough. But on the other hand, like, since you are allowing the gauge parameter to depend on psi in any which way,
right?
Why does it matter whether there's an equation of piece?
So that's why we said it's a genuine gauge transformation, and this is a trivial gauge transformation. An action at classical level is invariant under this kind of transformation that we observe when we discuss the general gauge algebra, right? We just wanted to see that that actually happens in string field theory, right? In fact, in full gauge, from the point of view of full gauge transformations, this kind of transformation is also a gauge transformation, like this kind of a piece, which actually which can happen even in.
The question is about this, what you are calling open algebra.
So the point is that this one you can think of as a pure genuine gauge transformation, right?
Okay.
So this is the kind of structure that you want.
Right.
So that's violated, clearly violated here, right? So you have psi L, omega 1, and this extra piece, right? That's why. So it's not like the usual gauge transformation. It's a piece that vanishes only on shell, but the structure, if you compare the usual or the general gauge transformation that you allow, it won't fit to that structure. So that's the reason. So that's a thing. So what you have to remember is that you can't use the usual quantization method for quantizing string field theory just by looking at the gauge algebra. Now let us move ahead, and then you can easily write down the quantum BB-master equation, BB-master action. Again, you will have a similar action with a simple generalization. So here you have a quantum action that's given by a two sums. So you have to start with multilinear function that's defined on a genus G Riemann surface. Then sum over all the number of insertions. Then you have to sum over all possible genuses or all possible loops that you can have. So if I set G equal to 0, you go back to the classical action. Once you have quantum action, you have to consider interactions that has loops in it. So that's slightly different from what you usually see in quantum field theory. In quantum field theory, you don't have interactions that have loops in it, right? So you don't have fundamental interactions having loops. You are supposed to construct all the loops from your interactions, right? So that you have basic interactions. But here, what you see is that you will start seeing interaction pieces in the action itself. You start seeing loops. If
I'm thinking of this linear product as
right,
string amplitude.
uh-huh.
Genus G.
Right.
So you can just write the action into write on that.
Yeah, you need that.
Find out that this.
Right.
That string correlation function.
String correlation function at genus G level itself.
Write the action.
Right. So that's the difference. I mean, that was a simplification in Witten's open string field theory. In Witten's open string field theory, you just require a cubic interaction, and you can reproduce all the loop amplitude. Now, if you try to do similar thing in at least following this formalism in closed string theory, you won't be able to create the full genus G loop amplitude in string perturbation theory using interactions involving genus 0. So that's a main complication or main difference. So in some sense, you can think of these as counter terms. So these counter terms are the one which remove all the UV divergences in string theory, at least in closed string theory. So this is a complete quantum action, which is consistent. You consistently put in a path integral. So you can take this action and then define your full partition function. And then sum over all the fields and anti-fields with a gauge condition. So it's a completely consistent path integral. But to construct that, you have to include all these high interactions, so infinite number of interactions. So you have a nice form, then like Sujay was saying, I mean, it's not so easy to construct. And that's the main reason why it's very hard to get any non-trivial information or quantitative information from closed string theory. In Witten's open string theory, you had a simple cubic interaction which you could evaluate. And then you can study the equation of motion and study its potential. But you can try to do same thing even for the closed string theory. The action looks so complicated, so it seems very hard to get anything or any quantitative information. But at the moment, you can think of having an action for string theory. And then the point is that if you want to study some formal properties of string theory or closed string theory, such as unitarity or analyticity, so all those things can be proved by using the fact that, or even soft theorems, you can prove using the fact that you have an action. You have a consistent quantum field theory. So you can borrow the intuition from quantum field theory. And moreover, you have to construct these multilinear functions to really write down off-shell amplitudes in string theory. Even if you are not going to use the full string field theory, if you want to write down scattering amplitude in string theory that is free from all infrared divergence, then you need to construct such amplitude. You might worry, I mean, it looks complicated, but you have to do similar thing even in quantum field theory, right? So if you want to regulate all the divergences, it's not so easy. Most of the time, you don't do 10 loop amplitude calculation. So that's the reason why. And in some sense, it's really nice. I mean, in single go, you produce the whole action, whole BV master action, right? So you remember, this is a very complicated quantum field theory, having infinite number of fields and extremely complicated algebra, infinite dimensional gauge algebra, which has extremely complicated gauge structure. It's not even guaranteed that you will be able to quantize it, right? At least formally, we quantized it. So that itself is a big success. So if you think about similar situation in higher spin field theory, you will realize, I mean, this is actually a big success. In higher spin field theory, you are even struggling to write down an action, even a classical action. So it's much better than that.
What is the main structure of gauge algebra for open string equation? Is it also an open algebra?
I think, I don't remember the precise. Is that right? At least if you want to learn more about it, I can say the mathematical name for this algebra. The algebra that comes in classical open string field theory is so-called A infinity. And the algebra that I described here is known as L infinity algebra at the classical level. At the quantum level, the L infinity algebra will be modified. It's even more complicated. So that's the formal discussions, and you can show that this action satisfies the quantum BV master equation. And that's an algebraic exercise. So now let us go to more non-trivial cases, or maybe I can just finish the discussion about the algebraic properties of closed string field theory by mentioning one more important fact.
Will you tell us how to construct this?
I will do that. In fact, that's the thing which I was trying to do using hyperbolic geometry. So far, what Barton has done is that he wrote down a formal expression for BV mass traction, and then the challenge is to realize it. So this is a construction based on certain assumptions. Right. So you assume that you can construct a string product or multilinear function satisfying fundamental identity. That's an assumption. So in some sense, so far whatever I have done is comparatively the easiest part of string field theory. Now the most complicated part or the challenging part is to construct explicitly what you mean by this multilinear function. How will you construct it? And to do that, he was trying to use the millimetric Riemann surfaces. So, and I was trying to do it from hyperbolic geometry point of view. So let me write down the BRZ identity or the BRZ transformation for SFT. So we can take a string field and then act with the fermionic operator S that's related to the BRZ transformation, and it's given by considering the anti-commutator or the anti-bracket that we defined. So you take the string field and then find the anti-commutator with the action. Then you have the parameter mu. And you can compute it, and it's given by, again, two sum over GNSS and sum over the punctures. With a string product. So this is the BRZ transformation. Now one can look what happens for the classical case. At classical level, you have to replace, you should restrict only to those cases where G is equal to 0. And you can see that if you look into the classical BRZ transformation, this is proportional to the equation of motion. So the field configuration is annihilated by BRZ transformation only if it satisfies the field equation. So this is the thing that you usually see in string perturbation theory. So if you want to have all the physical observable should satisfy the equation of motion. And this equation of motion can be thought of as the equation of motion that you impose for the target space field. So you should reproduce the Einstein equation here. Now, we didn't gauge fix the theory yet. So we had fields and anti-fields. Now we want to throw away the anti-fields. Now one of the convenient gauge is the so-called Siegel gauge. And in Siegel gauge, what you do is when we constructed string field theory, we started with field configuration that are annihilated by B0 minus and L0 minus, right? Now you have to impose one more condition. So you have to impose the condition that a string field should be annihilated by B0 plus also. So B0 plus and minus where the combination B0 plus or minus B0 bar. So if you impose that the string field satisfy or string field is annihilated by B0 plus as well, then you can throw away all the anti-fields. So that's one convenient gauge that people usually use. And within that gauge, if you fix or if you choose to work with Siegel gauge, you can find what is the form of propagator or what is the form of kinetic term. A kinetic term will take the following form. It's given by half of psi C0 minus C0 plus L0 plus psi. So this is a kinetic term in Siegel gauge. And if you choose some other gauge, then the kinetic term might be really different. And this means that the propagator or the string propagator in Siegel gauge looks like B0 minus B0 plus into delta L0 bar. So this is the level matching condition divided by L0 plus. So the string propagator in Siegel gauge looks like this. So now we have, so this is the algebraic part of string field theory. Now let us discuss how will we construct the multilinear function. How will we construct this bracket? So we can consider, say, string fields psi 1 to psi n. Then if you want to construct psi 1 to psi n associated with genus G Riemann surface by just considering the off-shell measure omega Gn. I will explain what you mean by off-shell measure. Constructed for string field psi 1 to psi n, and you can integrate this over a region in moduli space of genus G Riemann surface with n punctures. So mgn denotes the moduli space for Riemann surfaces having genus G and n punctures. And so this is a space having boundaries. You can compactify it and then get a compact space. So that's denoted by m bar. So this is the compactified moduli space for Riemann surfaces having genus G and n number of punctures. So you should think of nu Gn as a subregion, as a region inside the compactified moduli space. So consider a special region inside the moduli space and integrate the string measure over that region. And the claim is that this will produce the multilinear functions psi 1 to psi n g, which enters in the string field theory action. Now one has to remember that how you construct a string measure. So in the notion is that if you compute amplitudes for superstring theory, so the first thing to do is first construct a measure in the moduli space and then integrate the measure over the whole moduli space. Now this object that we construct is constructed using string fields. Now string fields won't satisfy an on-shell condition, right? So an off-shell or a generic string field consists of all those states, and some of them can be off-shell or some of them can be on-shell. So in general, you consider sum of infinite number of off-shell states. And off-shell states have some conformal dimension. So once you compute a correlation function for a operator having conformal dimension, then that object will start depending on spurious data such as coordinates on the Riemann surface. So this object that you construct, which you claimed as a measure in the moduli space, is not actually a measure in the moduli space. It's a measure in a higher dimensional space. And that means this object will start depending on more data than what is there in the moduli space, such as the choice of coordinates. So you have to choose a particular choice of coordinates for defining off-shell measure. So this is an important thing. We should choose a specific coordinate on the worldsheet and then compute the off-shell measure using the usual prescription. And once you compute such an off-shell measure, you should integrate over a region inside the moduli space, which I denote by nu gn. And this region, nu gn, is what usually called as string vertices. Now remember that this object cannot be an arbitrary object. So you don't, it seems like you can choose any choice of coordinate on the world sheet and then integrate over certain region inside the moduli space. But it has to satisfy the fundamental identity. So that is equivalent to saying that, so if you impose an identity on this object on the left hand side, it will impose or induce certain identities or certain conditions on the choice of coordinate that you can have on the Riemann surface, and also on the way you should choose the region inside the moduli space. So the way you construct string vertices, which is the collection of Riemann surfaces having certain choice of coordinates on each surface. So the string vertices has to satisfy a certain identity or certain constraints to make sure that the multilinear function that you construct using these string vertices satisfy the fundamental identity.
Can you just illustrate this for some specific case, say genus 0 or genus 1? See how this objects.
Oh, so this omega gn. So I will explain how to construct the measure in general. One can see how to construct it for simple case.
So what do you look for, say, this equals 0?
Yes, it's again look. It's almost like string amplitude calculation.
We can show you.
Actually, that's the main thing. Like I'm going to construct this object in detail. So let me explain how to construct off-shell measure. So off-shell measure omega gn, in some sense you can think of it as a differential form in moduli space having a dimension exactly equal to the dimension of moduli space. So the dimension of moduli space mgn is equal to 6g minus 6 plus 2n. So omega gn 6g minus 6 plus 2n is a top form on the moduli space. Now how you define it?
So for g equal to 0, or does it, I mean, if I said if g equal to 0 and n equal to 1 or 2, yeah, it will become negative. Yeah.
I mean those are the things which you don't consider.
Okay, so for g equal to 0,
so you have 2n minus 6 and you assume that should be greater than or equal to 0.
So that means on the sphere I should take at least
n equal to 3. Yeah, these are the non-trivial scattering amplitudes that you can have in string theory, right? And also you can have a propagator which has only 2 punctures, but that's fine. So you should think of, yeah, right.
the sphere 1 point functions will always have the means like what are the psi 1 etc. Take psi 1 comma psi 2 g equal to 0 0.
Right. So for the string propagator, although you have only 2 vertex insertions, you have BRZ operator inserted.
Oh, it has dimension is 0.
Yeah.
It means just a number.
N equal to 3. Right. So you don't have, you just have a single number. You don't have an integration over moduli space because you have a trivial moduli space. All the 3-point amplitudes are fixed by SL2C, right? It doesn't mean that like you have, I mean, still it can depend on the choice of coordinates. You may not have the.
Yeah, I guess that's what I mean. Let me see how the
Right. So omega gn is given by 2 pi I raised to minus 3g plus n. So this is a overall factor. Then you have to consider an inner product between a state which is known as surface state, and then you have the state or the set of string fields, and then there is an operator sandwiched in between these 2 states, which I denote by BQ, where Q is 6g minus 6 plus 2n. So you can think of BQ as an operator valued differential form having degree 6g minus 6 plus 2n, and then you are supposed to insert this operator valued differential form between two states. One is a state that's associated with a Riemann surface, and the other is the state that you are interested in. So, so let me explain what is RGN, and then I will explain what is BQ.
Phi is this psi 1 plus
Right,
psi n.
right. Phi is a tensor product between psi 1 to psi n. So this belongs to the Hilbert space, Hn. So what is a surface state? So this is a state that's associated with a specific Riemann surface. So let us start with a Riemann surface having genus G and n number of punctures. So let me consider such a surface. Say, assume that you have G number of holes and n number of punctures. So what one should do is, you can define a local coordinate. You should define a, first you identify a small neighborhood around each puncture, so which which can be thought of as certain disks. So you have n number of disks around each puncture, and we can introduce coordinates wi on each puncture. Now for computing the surface state, what we should do is, we should throw away all these disks, remove these disks. So we will get a surface like this. So we can denote this by RDGN. So this is a Riemann surface that you obtain by removing n number of disks around n number of punctures. Now what one should do is, you can perform a worldsheet path integral over the whole Riemann surface. And doing a path integral on a Riemann surface with boundary, or a surface with boundary, or even a manifold with boundary will induce a state on the boundary, right? And that state is what you call as RGN. So these are the states that you obtain by performing a worldsheet path integral over the Riemann surface with n number of such boundaries. So on these boundaries, you will have a particular state. So that's
All the information provided. You will see what was the boundary condition.
so like each, in other words, boundary condition can be related to a world state, right? So you perform a path integral and then come here. So that's a state, right? And that's sensible, because once you insert states here, so each disk comes with a state, right? So if you look into the ith disk, so which is like this, so you insert a operator here and then perform a worldsheet path integral, right? And that will induce another state, psi 1, psi I here, right? So that's a string field. And then if I contract one of the hole with this disk, so you are producing a correlation function, right? So that's the basic idea. So you have a path integral, or the numbers that you obtain by path integral can be thought of as a product between different states, right? Which can be thought of as splitting the manifold into two and then performing path integrals. So, and this is the basic idea people usually use in topological theories. So this is a state operator correspondence. So for RGN, you have a state operator correspondence by saying that you don't insert any operator on the worldsheet and then perform the path integral. Now once you insert this operator valued forms, you're slightly changing the states, right? So you should think of a worldsheet path integral or RDGN as a state, and that's what I mean by this. And you know how to construct phi. Now we should understand how to construct BQ. This is an operator valued Q form in the moduli space. So we can start with the moduli space MGN. So let us compactify it, and then we discussed that it should have dimension 6G minus 6 plus 2n. That means you need T1 to T6G minus 6 plus 2n number of real numbers to parameterize the moduli space. So you can think of this as a coordinate for the moduli space. So this is the coordinates on the moduli space. So these are real numbers, and by choosing a particular value for T1 to T6G minus 6 plus 2n, what you are doing is you are specifying the complex structure on Riemann surface having G number of handles and n number of punctures. So each point corresponds to a specific complex structure. On RGN. So by a complex structure, naively you can think of as a particular definition of DC and DC bar. Now one can ask, how can I move from a complex structure denoted by T1 to T6G minus 6 plus 2n to another point in the moduli space, which is T1 plus delta T1 to T6G minus 6 plus 2n delta T 6G minus 6 plus 2n. So how can we move in the moduli space? By starting from a Riemann surface RGN having a particular notion for complex coordinates. How will you deform the complex structure? So we are going to deform the complex structure by staying or by standing on a particular Riemann surface. So what you should do is you should find a coordinate transformation C bar to another coordinate C prime to C bar prime such that these coordinates are not related by an analytic coordinate transformation, right? So if you find a coordinate transformation where the transformation itself is not analytic, then that's equal to deforming the complex structure, and that will change the point in the moduli space from this to this, the other one. And there's a specific, and there's an object in the moduli space that does this. So that's the Beltrami differential. So you can think of starting from DC and then changing DC to DC prime, which is defined by DC plus some object into DC bar. So it has some index. And this mu is what you call as Beltrami differential. So this is a -1 differential that you define on the Riemann surface. So associated with each parameter, you have 6G minus.
These coordinates are all local or like they're subject to either?
You mean this coordinate?
The Z bar and G prime bar.
These are the coordinates that, so you can think of it like a global coordinate, or in each patch you can define a local coordinate with some specific gluing information. Anyway, you can define. Depending on how you how are you really representing your Riemann surface. You could start from I mean, there are different ways of representing Riemann surface. One is the representation where you start from the upper half plane and then define the Riemann surface. And there one can think of having a global coordinate with some certain regions in the upper half plane. Or in other words, you can, the other way is to just go to the full Riemann surface. So you could construct in any way and then split the Riemann surface into two different pieces, and on each piece you define a particular coordinate and then specify what is the transition function. So you can encode the information about the complex structure in the transition functions, or even in the full global coordinate with some particular parameters. So this is a certain differential that you construct in the moduli space. It's an object in the moduli space.
The second way that you mentioned, I think they want to think about this one to become on right. Split this into some different pieces. Then all the information about moduli space, you
That's true. So the point is that there is a specific way in which you can connect a mu c to this coordinates. So naively you can think of it like having a transition function and then taking derivative with respect to c bar. So if f is an analytic coordinate transformation, this is equal to 0. So if it is not an analytic coordinate transformation, then this is not equal to 0. So that's like having a non-trivial Beltrami differential. So you can localize all your information into the places where you do the gluing. So in fact, that's how Fenton and Nielsen defined Beltrami differentials. So they have a specific way of constructing Beltrami differential that's equivalent to saying that you have a specific way of deforming the complex structure. But the main point is that by staying within a Riemann surface, you can construct an object in the Riemann surface that has the capacity to deform the complex structure. So that's a Beltrami differential. And one can show that there are 6g minus 6 plus 2n number of independent Beltrami differentials that you can define on a GNSG Riemann surface with n punctures. And these are statements one can rigorously prove. So this way, when I do, we say that you deform the complex structure using Beltrami differential. When we go to this language where you have analytic coordinate, transition functions, so there people say that you do something called Schiffer variation, basically vary the transition function to change the coordinates or change the complex structure. So that these two are two viewpoints, and two viewpoints can be related. And I would like to depend on Beltrami differential. So once you have a Beltrami differential and a choice of coordinates, so you can associate a small variation that you do in the Modulus space to a particular differential. And a small variation that you do in a space is related to the tangent vectors, right? So in some sense, Beltrami differential can be thought of as a representation of tangent vectors in the Modulus space on the Riemann surface. So once you have all this information, you can introduce an operator BTI associated with the parameter moduli parameter TI. So how can I define this? So I start with the Beltrami differential mu c bar. Let's say that's associated with the parameter Ti, or basically mu c bar is related to or is the one which change the moduli parameter from Ti to Ti plus delta Ti. So take this Beltrami differential, multiply it with the BCC component. So this is the anti-ghost that you have in worldsheet CFT, and then integrate this object over the whole Riemann surface RGN plus the anti-holomorphic piece BC C bar mu C bar C Ti. So take the Beltrami differential, multiply with the anti-ghost, and then integrate over the whole Riemann surface. So this is the way you construct the operator BTA. So what you can see is that this object has the information about worldsheet CFT plus the information about the moduli space or the tangent space of moduli space. So that's why this object is a one form, operator valued one form, the moduli space. So you construct all these objects, and then one can take the following product. So BQ is defined as a product of BT1 to BT.
It doesn't say what's a one form in case. Is it because mu contains is mu a one form on this?
Yeah, so mu is like a differential form. Yeah, so I think I should, in some sense, I should multiply it with delta Ti. Yeah, I think. Most of the time we just bury it in this one, but what you should do is you should take mu CC and then multiply it with delta Ti. so that this is really a differential form, and it has all the properties, right? So this is, I claim that this is a differential form. That means when I anti-commute, when I try to swap the position of two different things, there should be a sign factor, right? So that's like a differential form, and it has that property. That's the reason why you have to multiply with the B. B anti-commutes. So delta T itself is not a differential form. It's a small variation, right? Generated by mu C, C bar. But the B is the thing which makes it a genuine differential form. So that's why you can think of it like a one operator valued one form. So yeah, I should explicitly mention this is equal to delta T into delta T. So you have to construct this object. For that you need to construct Beltrami differential, and that itself is a non-trivial task. You have to construct it explicitly. So if you consider random representation of Riemann surface, then it's not that easy to construct this object. But again, when you look into hyperbolic geometry, you have an explicit way of constructing this object.
So that is something that is fixed, right? Given a Riemann surface of genus G, which is whichever it is, like the different object.
It's a definite object that you can construct on the Riemann surface. So the first step is to construct this differential form. So if you are using some random representation of Riemann surface, you are supposed to construct it. Basically, construct the moduli space using that representative of Riemann surface.
So fields on the surface one is going to put, that depends on the theory that we have.
Yeah. So it depends on the world sheet CFT. And the point is that when you use this formulation, B cost and C cost are anywhere there. It doesn't depend on what kind of matter fields that you place. So the construction of the fundamental objects in the theory won't really depend on the matter field. You can formulate closed string field theory on any background.
So far the matter fields are the whatever field that I want hasn't come to.
No. So that will be there. That's somehow restricted to the string field itself. It won't enter psi 1 to psi n. It won't really enter into the basic construction. And the reason is simple. You don't associate any Gauss number to the matter field, right? Where matter field has 0 Gauss number, world sheet Gauss number. But B field and C field has Gauss number. And Gauss number conservation is related to the fact that you should integrate a particular object on the, you should integrate only the top form over the whole moduli space, right? So you construct a top form in the moduli space and then integrate it. So that's the reason why you always say that, that's associated with the fact that the Gauss number for the final correlation function should be 0. And that's something which you can find by just considering BC system on a Riemann surface and then find its anomaly. And you can see that the mismatch is always exactly equal to the number of dimension of the moduli space associated with the Riemann surface. So you just utilize that fact. So once you have all this information, then you can write down your multilinear function, and then you get the string field theory action. So what we have to do is, we have two things left. First of all, one thing is we want an explicit characterization of moduli space. We should choose a specific coordinate. At the end, the construction should be independent of the coordinate, but when you have to explicitly construct it, you have to specify what are the explicit parameters for your moduli space. And then associated with that parameter, one should construct what is the Beltrami differential on the Riemann surface.
So those things are basically completely mathematical.
Those are completely mathematical problem. And then on the top of it, you have to choose a specific coordinate.
That also is a
part of mathematical problem. And the next step is to really solve that mathematical problem. Choose. So you can solve it several ways, right? You could choose some particular parameterization, and you could choose some random coordinate on the Riemann surface. Right. So far, I just said that you can choose any coordinates on the moduli space, and then you have to construct the Beltrami differential, perfectly fine. Then you have to choose a coordinate on the moduli space. But everything has to satisfy fundamental identity. So you have to pick that kind of construction that is suitable for getting the.
Okay, where the mathematics is and the fields is
Yeah, so the
fundamental identity is it again like a part of this various or mathematical structure of this thing? So is it?
it's not guaranteed that any random such construction will follow the string field theory stringent condition. This fundamental identity.
Fundamentally, the physics input. That's the physics input.
Exactly. So the fundamental identity is a physics input. That means gauge invariance is a physics input, and that physics input will choose what particular way of choosing coordinate or what particular way of choosing local coordinates on the worldsheet CFT will preserve the gauge invariance, and that's something which one has to figure out. And that's the reason why Barton-Swieback proposes minimal area problem. So when you start with a Riemann surface having a particular metric, then he can show that the multilinear function that he constructs using that construction or that minimal area metric will lead you to a string product or multilinear function that which satisfy the fundamental identity.
You show like that as is there possible, for example, like say G equal to 0 is sphere with just some 4 punctures, the simplest non-trivial cases.
The point is that when you look into 3-punctured multilinear function.
In any case, it's the simplest to deal with, but never.
Right. So let me just mention that when you are interested in a case with where you have sphere with 3 puncture, you can choose any coordinate because there is no degeneration for this.
So I just want to say, okay, so the purely then involves differential modulus space.
Here nothing will come because it's a trivial.
Let's take that. Let's take non-trivial. Right. Let's take n equal to 4.
You choose n equal to 4, and then.
Like there will be 2-dimensional modulus space.
Right, you have a 2-dimensional modulus space, and then you have to choose a disk around 4 punctures and choose coordinates. Right. So, right. So when I choose a particular coordinate around these things, then I have to make sure that when it degenerates, it provides you 3 punctured spheres, right? And on the 3-punctured sphere also, I start with some coordinates, say C1 to C2, C3. So whatever fundamental object that I have to choose coordinates on it, right? And the way I choose the coordinate should be such that when the higher point function degenerate, that should give you the lower point function with exactly same coordinates as you already had. And choosing such a coordinate system is not a trivial thing.
Has this been solved for 4-point function?
For 4-point function at the tree level, things are simple. So you can use something called SL2C maps on the complex plane to resolve this. So that procedure is iterative. So you start with some coordinate, and then propose another coordinate here, and then do the degeneration. You may see that it might match the coordinates that you chose on 3-point function may match with the degeneration, or sometimes it may not match. If it is not matching, what they do is they just correct the coordinates on the 4-punctured sphere. And you have to continue this for a Riemann surface, say at classical level, to infinite number of punctures.
No, that's for just for G equal to 0 and equal to 4. It's just a question of choosing this
appropriate coordinate, right?
Such that like what you mentioned, like another degeneration.
Right.
So that is okay, a problem.
So that's a problem. That by solving that itself,
Just a mathematical.
That's a mathematical problem. That's true. Actually, that's what is left, right? So you had to solve the mathematical problem.
So that's what you're also saying is the physics.
Yeah, because this degeneration thing.
Let me take, okay, there is even simple case like that. If I take G equal to 1 as a total, so it's just 1 puncture, right? That one. Okay. So there it seems like I should be able to do whatever choosing the coordinates.
Right, you can, and people have done it in different ways, at least 3 ways I know. So you can choose a coordinate here, and then when it degenerates, it gives you thrice punctured sphere. Right? Again, this coordinate should match with the coordinates that you had here.
So is that the same as the fundamental identity you're saying? So can we understand this? Can we show this out?
Yeah, I will describe that. So I thought of describing it in a systematic way.
When you put the physics input, you should also decide what kinds of fields you can do.
So when you do the algebraic manipulation, everything will be you take care of all those issues.
No, so the kind of fields and the type of field that you have to put in, like you dictate by this or
So that's why I'm saying all those informations are hidden in the string field, and when you decided what is your string field, I mean you are done. And those details will not come into this this part.
So this is not
the physics is not. I mean the gauge invariance will not determine what kind of matter fields that you can use. The gauge invariance will just tell you how to really construct this construction. I mean basic interaction.
There is no principle that will tell you what kind of fields are how.
I mean, there are constraints coming from the fact that whether
that's solve the equation, the quantum mass action, right? QB or whatever.
Yeah, that construction itself depends on the worldsheet construction, right? And the worldsheet construction is possible only if you choose some particular dimension. Critical dimension is important, right? Only then you can reduce the whole problem to moduli space and this certain local coordinates.
If you start with the standard sigma model, we have three fields. I expect you have a whole series of fields that I already know. Right. But here you are saying that even that much information.
No, the point is that's needed because I mean to have a world. Right. Actually, that's what I'm saying. Although this is a quantum field theory, this is a quantum field theory that you get from the sigma model kind of description. Yeah, it's worldsheeted. So you have a particular string perturbation theory, and for that string perturbation theory, you can construct the string field theory. And for constructing string perturbation theory, you should make sure that there is no anomalies. Only then you can define a consistent description of in terms of moduli space and Riemann surface. The problem will be reduced to Riemann surface only if there is no anomaly, right? That requires to have a particular dimension.
Then to decide whether there is anomaly or not, there is how to go about it. Like if I have to go to sigma model for all these things, and then they come back to things. So what is this?
So infrared divergence, that's the main thing, right? I mean, for the perturbative point of view, that is the thing, and that is the big thing.
I was thinking more the field contents. The field contents only. The field contents in the various or field voltage, this voltage, that voltage.
So maybe one can push it higher. I mean that's equivalent to saying that you solve the theory and see what are the symmetries, allowed symmetries are there, like what are the non-perturbative symmetries.
But again, if you don't even know the picture level, if this approach or at least to even the field contents, what kind of fields we have, even if you have to code this.
You see, if you should think of like having a consistent quantum field theory, right? You have a general construction of quantum field theory. And general construction won't tell you what particular kind of field theory that you can choose. You can choose any Lagrangian, right? So choosing a worldsheet CFT is exactly equal to choosing a particular Lagrangian for your theory, right? So quantum field theory is not a...
String theory is supposed to be special and it is supposed to give everything.
No, I think string theory is a framework. You have to choose your theory, right? Although I call it a string field theory, it's a string field framework. It's like quantum field framework. And choosing a worldsheet CFT is exactly equal to choosing a Lagrangian in quantum field theory. So choosing particular Lagrangian won't really matter. It's basically the general symmetry. Structure of the thing is the main thing that will go into the quantization. So maybe I will describe it in a systematic way. Okay. So to do it in a systematic way, I should introduce what you mean by, let us start with the propagator itself. How will you construct propagators? Then the propagator is the thing which dictates what should be the interaction, right? Because when you look into the action has a kinetic term that has propagator in it. I mean, that's what gives you the propagator. Then you have all series of interaction terms, right? And the interaction terms in action has a property that is something which doesn't contain a propagator in it, right? So in the basic interaction doesn't have any propagator within it. That means you can't construct the basic interaction by gluing a Feynman diagram. So that is the basic input that you need. So you need to first choose what you mean by your propagator. Then you can try to define what you mean by fundamental interaction. Fundamental interactions are all those interactions that can't be constructed using different Feynman diagrams and gluing them with the propagator.
So in terms of Riemann surface, the propagator is like a cylinder and this is like a band.
Yeah. So that's a naive idea. So I have to explicitly mention what do I mean by a cylinder. So that requires discussing the plumping fixture construction. So consider two Riemann surfaces R G1 G1N1 and RG2N2. So you have Riemann surface having genus G1 and Riemann surface having genus G2 with punctures N1 and N2. So I have a picture like this. So let me choose coordinates on RG1N1 as W1J. So let's say you have a jth puncture. So my coordinate is W1J. And in the RG2N2 surface, the kth puncture has coordinate WK2. So I am looking to the jth puncture of Riemann surface RG1N1 and the kth puncture of the Riemann surface RG2N2. So I can choose a small disk around these two punctures. So disk 1 and disk 2. Here I have coordinate WJ1 and here I have coordinate WK2. So you have two disks D1 and D2 with coordinates WJ1 and WK2. Once you have this, you would like to glue them. What do I mean by gluing? When I say I am gluing, what we mean is we identify disk with a particular coordinate transformation, right? So before doing the coordinate transformation, what we should do is let's choose a disk within the disk and remove these disks. So this is a disk which has a particular radius measured with respect to this coordinate. Let's say we have a small disk having a radius less than mod t. And then again from here, I choose a region having a particular radius. Again, same radius.
So it is.
So
this B1 and B2 are one that you kind of cut off.
Right. So I get from here, and then from the point of view of coordinates, W1 is just a disk, right? And then I remove a smaller disk having radius root t, mod of t, where t is a complex number e raised to minus s plus I theta, and s can be anything between 0 and infinity. And theta is between 2 pi and 0. So mod of t is going to be definitely less than 1. And with respect to this coordinate, this disk has a radius 1. So you choose a unit disk around the puncture from two Riemann surfaces, remove it, place it somewhere, and then again remove another disk having a radius mod t. And then you have two annuli. You identify these two annuli by specifying a particular transition function. So the coordinate wj1 is related to the coordinate wk2 on this by the relation t by wk2. So basically that's equivalent to saying that you have wj1 into wk2 should be equal to t, and t is given by e raised to minus s plus I theta. So you are identifying two annuli. So that's equivalent to removing the cusp region from here and then identify them. So you get a Riemann surface having a plumping collar like this. So the two Riemann surfaces at the end will be joined. So you get a Riemann surface R G1 plus G2 with N1 plus N2 minus 2. This is your new Riemann surface. So the plumping fixture, this particular construction gives you a way of gluing two Riemann surfaces. And when you demand the following, that so you think of all the, so you obtain a collar here, right, after the plumbing fixture. So we can call that collar as plumbing collar. So this plumbing collar is exactly these two annuli with this identification. And all such plumbing collars are the thing we think of as string propagators. So in other words, when we consider CFT on this collar and then integrate that CFT from S ds from 0 to infinity and theta from 0 to 2 pi, and with this worldsheet CFT, you will produce a factor 1 by L0 bar, 1 L0 plus L0 bar with this extra factors B0 plus B0 minus and delta L0 minus. This is a level matching condition divided by L0 plus L0 bar. So I am integrating over S and theta, where S and theta runs from 0 to infinity, 0 to 2 pi. Oh, so you have the worldsheet CFT itself here. So let's say you have a worldsheet CFT on this glued surface, and then just restrict to the CFT on this annuli, and then perform the path integral. Just perform the path integral, full path integral. That will produce a factor B0 plus B0 minus divided by L0 plus L0 bar. So it's again like the surface state business that we discussed. So when you do the path integral, you produce a surface state, and then across, so you have a state here and here, right? So you can sandwich the states between two states in the string Hilbert space. So that will produce this factor. So when I insert that between two states, phi phi, so that will give you 1 by k square plus m square, right? And that's what you expect for a propagator. So the plumbing fixture construction introduces the string propagator.
No, I understand what you should get. I just understand how you see that there's a possibility.
Yeah, that's what I was trying to explain. So let's look into the plumbing collar, which can be thought of as an annulus, right? And then you just perform your path integral, worldsheet CFT path integral over this. Before we discussed that, sometime back, you produce a surface state associated with the annulus, right? So which we can call as A. So you should think of that as an inner, Beckett and Bra, right? A1 and A2 corresponds to two boundaries. So now, so that's an object that you have, and you should think of this object. You will see, one can see that that object is precisely 1 by L0 plus L0 bar. This is something you can work out and see. And when I take the inner product between these two, I should get a number, and that number is 1 by k square plus m square. So that's the notion of, that means one can identify the plumbing fixture construction as the propagator for string field theory. So in other words, what one can do is, so you have 1 by k square plus m square as propagator in quantum field theory, right? And then you can represent that as e raised to minus s k square plus m square with ds running from 0 to infinity. This is a Schrödinger representation of propagator. So actually what you produce is analog of Schrödinger representation of propagator in string theory. So the gluing parameter s is there even in quantum field theory. Theta is not there because you don't have a string to rotate it, right? So shrinking theta to 0 is analogous to taking a point particle limit. So it has a correct point particle interpretation. So that's why plumbing fixture construction is the, we should identify this as the propagator or string propagator. And this is the propagator that we are going to use for string field theory. From the geometry point of view, this.
But there's the only natural choice, right? There is no other choice.
In Siegel Gauge. In Siegel Gauge, this is only natural choice. You could have different kind of gluing.
So if you have closed chain and it is populating, also it will like a closed chain will populate.
Right. So that picture is unique. It looks like that's the only way you can have a propagator in string theory. But here I mentioned that I'm going to use a particular gluing, right? my gluing transition function has a particular form. And this particular transition function will provide you the propagator that you get in Siegel Gauge. Now, if I change this gluing, I may get a propagator, but in a different looking propagator. And one may show that that new propagator corresponds to different gauge fixing of string field theory. So that's why I'm saying this is one way of getting string propagator. And I'm going to use that propagator. So Sujay, I have time or?
We have 5 minutes.
So we identified what you mean by string propagator. Now when you so this fact is important for defining what you mean by string vertices. So we said that the interaction term that comes in the string field theory action should not have any propagator in it, right? And how you get the string interaction term? So the multilinear function is obtained by integrating the optional measure over a collection of Riemann surfaces, right? And if you read this fact together with the basic need that the interaction term should not have any propagator in it, that's equivalent to saying that the collection of Riemann surfaces that form the string vertices should not have any Riemann surface that can be obtained by the plumping fixture of 2 Riemann surfaces, right? Yeah, that defines your new GN. I mean, one fact of, that's one part of new GN. So here what we are trying to do is, we are trying to identify what is the region inside the moduli space, where this one is the compactified moduli space. You are trying to identify a small region inside the moduli space and trying to identify that with the string vertex. And what one can see is that this is a construction by Mumford, and when I take S going to infinity limit, that's equivalent to saying that T goes to 0. So where I have an identification W1 into W2 equal to 0, right? So when I do that kind of identification, then what I produce a Riemann surface, not a genuine Riemann surface. It's a Riemann surface having degeneration in it, right? A degenerate Riemann surface is obtained by gluing 2 Riemann surface with this identification. And these are the Riemann surface that comes in the boundary of the moduli space. So first we identify that we should remove all the Riemann surfaces from nu Gn that comes from the boundary of the moduli space. There should not be any Riemann surface that's close to the degeneration. So at least if you think of nu Gn as a connected space in the moduli space, there should be a neighborhood between the boundary of the moduli space and the boundary of the string vertex. So this is the boundary of the moduli space, which is del m, and say you have the boundary of the string vertex del nu, there should be a gap between these two. So that is the first condition. So let's look into the case M04. So this is the moduli space of Riemann surfaces with 0 genus and 4 punctures. So it's a 2-dimensional region, and that has 3 boundaries, corresponds to X channel, U channel, and T channel, right? So I can represent M04 as a thing which looks like a pair of pants. So the region here I can identify as nu 04, and the region, so I have 3 legs, right? And one leg I can identify with a S channel, the other one I can identify with a T channel, and the third leg can be identified with a U channel. I mean, T channel or a U channel, right? And here nu 04 can be identified as a 4-point interaction with no propagator in it. So you see that, I mean, naively it looks like if you can find string vertices having the following property. So let's say you start with the string vertex nu Gn. So this is the string vertex that you define at, for interactions having G loops and N external states. And I said that we have this construction, this plumping fixture construction. So there are certain Riemann surfaces that can't be constructed using plumping fixture. Now there are Riemann surfaces inside the moduli space that can be constructed with plumping fixture, right? So let's say I have one number of plumping location. Then I denote that kind of Riemann surface as Gn1, let's say. And then I can continue this procedure and I can obtain Riemann surfaces having 3g minus 3 plus n number of plumbing locations. So that means these are Riemann surfaces having 3g minus 3 plus n number of propagators in it. So these subspaces inside the moduli space. So the V0 for 1 composed of these 3 regions. So these 3 legs, right? So these legs makes a subspace inside the moduli space, which I denote by VGNI, where I denotes the number of propagators in it. And together with the fundamental interaction, basically the string vertex, the whole, so this can be thought of as Feynman diagrams, right? VGNI can be thought of as a Feynman diagram because that's something which you obtain by gluing the string vertices with a propagator. So the string vertex together with the whole.
All possible degenerations of the
Right. So you have to remove all the degenerations, right? So that part is what you call a string vertex. And the condition for getting a multilinear function that satisfies fundamental identity is that the string vertex should have the property that it should cover the whole moduli space once together with the Feynman diagrams. So you have a fundamental interaction string vertices and the Feynman diagrams obtained by gluing different string vertices with a propagator or with some number of propagators. They together should give you a single cover of the moduli, compactified moduli space. So and remember that when I defined string vertex, it's important that it's a collection of Riemann surface together with a certain choice of coordinates in it. So that's what I mean by a string vertex. A string vertex is a collection of Riemann surfaces with a choice of local coordinates on it such that none of the Riemann surfaces that belongs to string vertex has degeneration in it, and on the top of it, it should satisfy the condition that the coordinates that you define for the Riemann surfaces that belongs to the boundary of the string vertex should match with the coordinates that are induced on the glued surface that belongs to the neighborhood of Riemann surface, which I can obtain by gluing with a propagator having 0 length. So here I can, so if I go this way, I start getting Riemann surfaces having string propagator with infinite length, right? Now once I come close to the boundary of the string vertex, I start seeing Riemann surfaces having propagators with 0 length. So the boundary region can be either thought of as a boundary of the string vertex or as the Riemann surface having 0 length propagator. And what you demand is that you just need a continuity requirement. So the choice of coordinates that you have on the Riemann surface that's inside the moduli space should be continuously changed to the choice of local coordinates that you get by gluing different Riemann surfaces. So that's a continuity condition across the boundary of the modulus, boundary of the string vertex. And if you can demand that, that guarantees that the multilinear function is going to satisfy fundamental identity. So that's the basic observation. So that's why I keep on saying that the conditions on the local coordinates is basically comes from the gauge invariance requirement. So then now next lecture I will show that you can obtain or you can choose choice of local or a particular class of local coordinates using hyperbolic geometry, and that will satisfy this continuity condition up to some error, which that's why people were not able to use choice of hyperbolic geometry for constructing string field theory. If you naively look at it, you see that you won't be able to construct string field theory. But with some appropriate modification, the structure of hyperbolic geometry says that you can get a string field theory. It's almost an approximate construction, but approximate in some sense. But you will get, in some limit, you will get consistent answers.
So you have a nice new GN.
Right. You have a nice GN. Yeah. You can construct every single Riemann surface in that new GN. Explicitly, it's not in principle construction. You can explicitly mention what do I mean by local coordinates, and this construction is a construction that's valid for any level. So you can do that for an arbitrary GNN, and that's completely solved the whole problem. It's single way. and that's highly useful for doing explicit calculation on the moduli space. So that means it's a single step that solves almost all the thing, at least in principle. That there is a theory there's a well-defined or well-developed mathematical theory that can be used to compute things in string perturbation theory or in string field theory. That's it.